Okay, so good morning everyone. Today is my last day here. I hope that you enjoyed your first week here at the summer school, and I hope you learned something from my lectures and from the contests. Okay, today I decided against the problem discussion, and instead I'm going to talk about geometry algorithms, since geometry algorithms are hard, and everywhere I go, everyone tells me that the weak spot is geometry. Right? So, wonder if you think about yourself that way. So, I can't solve geometry problems. So, today I'll try to explain how geometry algorithms can be implemented and what are the advices on how to implement geometry problems. Today I talked with some of you, yesterday we talked with some of you about some geometry, so I thought that I expand that into the full lecture. Okay, so geometry for today. Well, I think you know about most of the basic primitives, like we store points as just a structure of two doubles or two ints. We have scalar product. This can be turned into the primitive, which tells us, okay, does this point, so we have the point and the normal vector, does any other point lie into this half plane, inside this half plane? Or basically, if you have a line or a point in the direction, does this point have a positive projection? So scalar product is basically the projection of AB and C. So the scalar product of AB and AC is basically the length of the projection of AC onto this line times the length of this vector. Right? And if you didn't know, then it's equal to length of A times length of B times the cosine alpha. Well, this is alpha. So the same for vector product. It's a lot of geometry can be done in just with simple algebra, like just manipulating the formulas. So the easiest way to remember, at least for me, the vector product is that it's just a determinant 2 by 2 of matrix AX, AI, BX, BY. So X, BY, so the cross product rule, minus AY, BX. And so this is one of the most important primitives there is in geometry. It tells us, so we have basically 2 points. Again, 2 points can be we can view these 2 points as a half plane. So everything to the left of this vector, well, when we draw it from this point, has positive. So A, B, C. Here, the vector product AB times AC is positive. If 3 points are on the same line, it's 0, and on the other, it's negative. And a lot of standard stuff can be expressed in terms of vector products. Okay, so we talked about this already. So the line equation is ax plus by plus c is 0. The half plane equation is greater than or equal to 0. So the half plane is all these points that we have some designated point and we have a direction, and they are in this half plane. So this is the normal vector AB. So basically all the points that have positive scalar product with the normal vector are in the half plane. And let's quickly remember how to intersect two lines. So we have A1, B1, C1, A2, B2, C2. So the most convenient thing for me here is to use Cramer's rule. So we compute the 2x2 determinants of basically of these two normals, and if normals are not, well, if two normals of two lines are not parallel, so for example these two are not, then they intersect at exactly 1 point. And if it's 0, so if the cross product of two normal vectors is 0, then we have some chances. So maybe these two lines are the same. This means that the intersection of these two lines is the entire line, and maybe it's empty if they are parallel but don't have any common points. So the determinant is A1, B1, A2, B2. So basically this is the system of two linear equations. We can draw it. We can say that it's equal to minus C1 minus C2. Then, so if it's not 0, then I calculate the x. So basically instead of a's, I plug the right side. So it's minus C1 B1 minus C2 B2. And I think the easier way for me to remember is to swap the columns. So swapping the columns changes the sign, and I will remove this minus. So it's B1 C1 B2 C2. And the same for the other one. So I plug minus C1 minus C2 instead of B1 and B2. I get A1 minus C1, A2 minus C2. And again, I'll swap two columns and remove this minus. So I get C1, A1, C2, A2. And you can notice that these three determinants are pretty similar, right? So it's AB, this is BC, and this is CA. So the next determinant is, well, you can write the next determinant as a cyclic shift of all variables from another. So D is AB, dx is, we replace A by B, we replace B by C, so we get the dx, And to get the dy, we replace b by c and c by a. So I think this is an easy way to remember all these formulas. And the final result is dx divided by d and dy divided by d. Okay, so let's talk about convex hulls. So I'm sure you already know how to calculate the convex hull. Please raise your hand if you find the minimum point, then sort by angle, then do the Graham scan. Okay, and what do others do? Yes, so I think the more convenient way is to sort the points not by angle, well, like finding the minimum point with minimum x and among those with the minimum y, and then sorting by angle. And to sort by angle, you should use vector product. I think it's less convenient since, well, you'll have to write a lot of different code. While I think this algorithm is a little bit simpler, and I always implement it myself. So let's sort points just as pairs. So I'll just sort the points as pairs. So first I sort by x, then in case some points have an equal x, I'll sort by y. So I get points so I just go over all points from left to right. So let's see what happens if I run the normal scan. So if you remember the scan, so I keep a stack of all the points in the current convex hull. Then I add the new point, while 2 points in the stack and this point are a bad pair. So this means that they form the right turn. So we have a situation like this. We remove the middle point. So we remove the last point from the stack. So let's see what happens when we work with this set of points in this order. So first we add this point, then we add this point, then we add this point. Then we look at these 3 points. These form a bad pair since this is a right turn. So we remove this point from the convex hull. Instead we have these 4, then we add this one, then we remove this one. Add this one, remove this one, remove this one. We get this one, this one, this one. So what we got, instead of sorting by angle, we sort just as pairs in lexicographical order. This might be convenient if you store your points as pairs of int and int, since this is the standard comparison function that is already defined for pairs. So you don't need to do any additional code. I don't advise that you do, but in simpler geometry problems, it might be easier to just store them in pairs and don't have a special sort function. But if you have a more complicated geometry problem, I think it's better to have designated structure for these points. So we found the lower convex hull of these points. And if we do the same, but we go over all points from right to left, we get the upper convex hull. So now we can combine these two the lower convex hull and the upper convex hull, and then we can get to the result. I think this approach, well, it's pretty similar to sorting, but you don't need to sort by angle, which is a bug-prone place in your code. So you can easily mess up the signs, or you can easily forget, mess up the order of points, for example, or you have to have special code for finding the leftmost bottom point. And there is one more advantage that I can think of, is that if we need to build the convex hull multiple times for different sets of points, then we don't need to sort points all the time from scratch. So we can sort all the points by x and y in the beginning, and then we just take some subset of points. So for example, if we're doing some kind of divide and conquer on the list of points, so there is a divide and conquer algorithm for building a convex hull, for example. And maybe we're doing some more complicated thing with the set of points, so we divide them by x, then we need to do something with the convex hull on the left, do something with the convex hull on the right, and somehow combine the results. And we don't need to sort the points at every step. So if we sort them as pairs, then we already have a sorted array on the left, we already have the sorted array on the right, and this scan with the stack takes the linear time, while the sorting takes n log n time. So this even might be an asymptotic improvement to the program. Okay. A lot of geometric algorithms use the property that this is a convex hull. And there is one problem that is pretty famous, but I think there is a lot of confusion with how to solve this problem. So this problem is called a diameter of a point set. And of course the diameter is 2 points with the largest distance. So we have the set of points, and we want to find the 2 points that have the largest distance between them. So, of course, the first step is to solve for a convex hull, since if we have some point inside of convex hull, it cannot be the answer. Since we can find the point on the convex hull, we can replace this point inside the convex hull. For example, if this was the larger distance, this is not. This is the larger. So for each point inside, we can replace it with some other point on the convex hull where the distance is greater. Okay, so what is the algorithm to, if we have the convex hull, what is the algorithm to find the 2 farthest points on the convex hull? Well, it's 2 pointers, right? So we start with some point, so let's enumerate these points in counterclockwise order. And for each point, let's keep track of the farthest point from that one. So for example, for this one, this will be this point here, and we check, is this the larger distance? So we're going to find the maximum result. After we move counterclockwise, this point will also move counterclockwise. So it's a linear time algorithm with 2 pointers. it's not the correct one. Because if you measure distance from this point to all other points, it's not a bitonic function. So to be able to use 2 pointers, your function has to first increase, then decrease, and it's not true for distance, even in case of convex polygon. So let me draw this kind of example. So I have this first point here, I have the second point, fourth point. So these are approximately the same distance, so I can draw a circle through them, which this is the center. And so I can just put the third point inside the circle. This will be still a convex polygon. But as you see, the distance here is large, then small, then large, and we can make as many of these alterations as we want. Right? So we can put another point here, and we can put another point here, here. So it can be larger, smaller, as many times as we want. So this is not the correct algorithm. The correct algorithm is as follows. So instead of trying to find what is the farthest point from this current point, we'll look at the lines that form our polygon instead. So first of all, we'll find what is the farthest point from this line. And comparing 2 points, so if I like to compare the distance from this point to this line, and from this point to this line, comparing 2 distances can be done again with vector product. Since vector product is also an area of a triangle, it's a signed area, so if it's positive, then it's equal to twice the area of the triangle, and if it's negative, then it's equal to minus 2 times the area of the triangle, and it depends on orientation of the triangle. So these triangles, basically, if the best rotation is counterclockwise, then the vector product is positive, and if it's clockwise, then it's negative. So this is the positive angle, and this is the negative angle. So how do we compare? Well, we know that the area of the triangle is its height times the base divided by 2. So we have the same base here. So to compare heights, we can just compare to. So we can just compare two heights of the triangle using the area of this triangle and this one. So we calculate the area of this triangle, this triangle. This is just a vector product, 1, 2 times 1, 3. It will be less than 1, 2 times 1, 4. So we move the point. And after we found the farthest point from this line, we check 2 distances. So we check distance 1, 4 and distance 2, 4. And we do the same for all sides of the polygon. It's still linear time, but we do more comparison, but now it's correct. Since the distance between the distance from point of the polygon to this line is necessarily always increasing and decreasing. It cannot, so for each line, it cannot first increase, then decrease, then increase again. So in this case, this is not a convex polygon. And there's one more point where we have to prove that we actually found the result. can prove that by a technique called the rotating calipers. I already talked about it during the analysis of the first day. So there was a problem that involved finding the smallest rectangle that encloses all these points. And again, we used a similar technique. So in general, rotating calipers works like this. So we have a polygon, a convex polygon. And we would like to enclose the polygon into between two parallel lines. So we have this parallel line. So the base point is this one, and the direction of this line is the vector, and the parallel line is here. So it has this point and the opposite direction. For example, the finding of the diameter is the same as finding the smallest distance between these two parallel lines. Sorry, the largest distance between these two parallel lines. And this will happen when two lines are based on some point, and this angle should be the right angle. So in case of general set of points, we'll have this line and this line, not like this. This line, this line. So this should be, well, this is approximately the right angle. So this is the largest distance between parallel lines that enclose our convex polygon. And in general, these rotating calipers work as follows. So we have 2 points, and the direction vector goes into this direction for the first line and the opposite direction for the second line. Then we're looking for the smaller angle of these two. So we're looking at the next side of the polygon for each of the lines. We take the smallest angle of these two, then we move our lines to look like something like this. So now, here, this is still the base point for this line, but for the other line, the base point has moved to the next one. And a lot of interesting things can be done with rotating calipers. For example, we can find common tangents of two polygons. So we have the first polygon, we have the second one. I would like to find the common tangents, so the line. So basically the extreme line where two polygons lie to the right of this line and to the left. So this can be done with rotating calipers, but instead of using just one polygon, we use vertices of both polygons. So we have a vertex somewhere here and the line, and basically whenever a caliper changes this base point from one polygon to another, this is where we find the common tangent. We can also find the common, like this is the common outer tangent, and we can also find the common inner tangent, like this one and this one. This can be done by rotating calipers in basically the opposite direction. So this one moves around the first polygon, this one moves around the second polygon in other direction, and whenever they meet, then we have a common tangent. Of course, if they intersect, there are no common tangents. But if two convex figures don't intersect, they can be separated by a line. So this is how you can find this kind of line. Okay, so let's talk about circles. Well, circles appear a lot in geometry. So the circle is, so we have a center and the distance from some point to center that is equal to the radius. This is the circle. So there are common primitives, like how do we check if two circles intersect? Well, we have to check if the distance between them is smaller than the sum of their radius. How do we intersect? Well, let's intersect a circle and the line. There are two common ways when we talk about circles. We can solve them with algebra or we can solve them with geometry. I'll show the both ways and you can choose which one you like more. So we have this line. So it's ax plus by plus c 0. This is x minus cx squared plus y minus cy squared is r squared. So, and we would like to find these two intersection points. First of all, let's do it in the geometric way. So, first of all, let's find if these two intersect at all. So, how do we check? Well, I have to check if the distance from this point to its projection on the line is greater than r or not. How do I find the projection of the point on the line? Well, I can just find the distance, right? So the distance from C to line, so let's call this line L, is I just plug Cx and Cy into this equation. If you remember, this line equation looks like this. So the scalar product of some point, so for some point P on the line, and the normal vector n of this line, which is just AB, this scalar product should be 0. Right? So these two vectors have to be perpendicular, but we can also use the scalar product to find the distance, right? So the distance squared is the same as scalar product of this vector onto itself. So this is just a Cx plus b Cy plus c. Well, and this might be positive, this might be negative. The sign of this indicates which side of the line the center is at. But if we take the modulo and we divide it by the length of this vector, a squared by b plus b squared, this is the distance from this point to the line. Let's call it h. So this will be basically the height of these two right triangles. Now I know h, I know r. So if h is greater than r, then there are no points. Otherwise, we can find this point. So if we have a line in the point, we can find the distance to that point we can find the distance between this point and this line, and we can also find the length. We can also find the projection itself. So to find the projection itself, we have to subtract the distance that we found times the normal vector. So we know that we can move from this point to this point by a parallel shift using this normal vector, and we know the distance. So we have to normalize the vector, and here where the sign distance helps. So we don't need to check if it's on this side, then we have to subtract, and if it's on this side, we have to add. Sign distance helps us. So the projection point, let's call it h large. H large is center minus the distance times the normalized normal vector. Sorry, normal. So it's ACX plus BCY plus C divided by square root of A squared plus B squared. So this is the sign distance, and we multiply it by the normalized normal vector. So AB divided by square root of A squared plus B squared. And usually the good idea in geometry, if you're checking for something and you can do it in integers, that's probably a good idea to do it. So we can rewrite this as C minus sign distance divided by A squared plus B squared times AB. So by the way, this also proves that projection of any integer point into the line with integer coefficients always gets you a rational point. Right? So you can't get a point with something like square root of 2. You will always get a rational point, and this is the formula. Okay, so we found h. Now we know this. This is square root of r squared minus h squared. And to get this vector, we have to rotate the normal vector 80 degrees. So we get minus b a. If you're doing this kind of geometry with the line, it's good idea to probably to normalize the normal vector in the beginning. So if you don't care about integers, so for example, you want to find the length of this intersection, and like, if you have a small error, this doesn't bother you at all. But if you want to find, just print 0 if line and circle intersect, and print 1 if these two intersect, you cannot have an error. So a very small error will lead to like the wrong answer, right? So if the line and circle are very close, you can have a small computational error, and this is why you will get wrong answer. So there are two kinds of problems. They are called stable and unstable. So stable problems are the problems where you need to print. Usually you need to print some real number. So for example, print the area of the intersection of two polygons, or print the length of some segment inside the polygon. So this is stable. Usually print real number, but not necessarily. So some problems where you have to print a real number, they are still unstable. And unstable usually have the discrete outputs. So print the number of points inside the polygon. On print yes if these two objects intersect, and no if they don't. This is unstable. So for stable problems, well, the stability is defined as if you change the input a little bit, the answer shouldn't change a lot. right? So pretty much the answer is a continuous function of the input. And in unstable, if the answer is discrete, for example, you can, like a small error in your computation can lead to large errors in, well, can lead to wrong answers. And usually here the output is discrete, but there are still some problems with the real output which are unstable. So for stable problems, it's usually fine to have all your computations in doubles or long doubles, and you can probably even use something like binary search or ternary search, like to find, I don't know, the best point, like the farthest point inside the polygon, or something like this, the point that minimizes the sum of distances, for example. And in unstable problems, you really have to be careful with your precisions, right? So if you get any computational error, so for example, here you divide, or b squared, sorry. Here you divide by square root, so calculating the square root introduces some kind of error, and dividing one double by another also introduces a square error. But the largest source of errors is, what do you think? What do you think is the largest source of errors in computational geometry and, well, if in just calculating with doubles? Not in just geometry, but also in probability problems. What do you think is the largest source of error that can arise?
Maybe square root.
Subtracting large states?
Yes. So let's remember what is the definition of the cross product or vector product. So AB is AX BY minus AY BX. So if these coordinates are very large, but the answer is very small, then calculating this in doubles can introduce a lot of error. So for example, let's look at these points. So A is 1 billion, 1 billion, 1 billion minus 1, and B is 1 billion plus 1 and 1 billion. So if you have these points, usually let's calculate this, right? So let's calculate what the vector product is. So it's 10 to the 9 times 10 to the 9 minus 10 to the 9 minus 1 times 10 to the 9 plus 1. And what's the result? 1. So this is the difference of squares. So it's 10 to the 9 squared minus 1 squared. So the result is 1. So this is if we look at this as a triangle, so we have 0, we have A somewhere, we have B somewhere. These coordinates are huge. So this is 1 billion, but the area of this triangle is 1. And if you calculate it in long doubles, well, it can work with 10 to the 9, but if I use some odd number, some other number rather than 10 to the power of 9, this will fail. So calculating this in long doubles will give you something approximate to 0 instead of just 1. So, and in general, subtracting large values will introduce a lot of relative error. So, if you have a large value with some error, and you have another large value with some error, when you subtract them, the absolute error is the same, but the result is much smaller. So the relative error just blows up. So you have to be careful when you are subtracting large things. And it's more of a problem when in probability problems. So it's more of an issue when in probability problems, so since like the formulas for some expected values, or when you do some kind of dynamic programming on like that involve probability, that involve expected value, usually you have some problems with where you subtract large values. So it's not enough to come up with a formula that solves the problem if your output is a real number. So sometimes there are problems with probabilities that ask you to output an integer p times q inverse mod m. And these are fine. You can't do other tricks with them. So for example, you can like drop some states from dynamic programming if the probability is 0. It is very small in that case. But you don't have any precision problems if you calculate the probability modulo m. Okay. So what was that all about? So in unstable problems, you want to be able to solve everything in integers. So you would like, if some condition can be checked in integers, you probably can do that. So for example, to check if a circle and a line intersect, you have to check if this distance is at most r. And to do that, you need to multiply both sides by the denominator. So it's r times a squared plus b squared. Then you raise it all to the second power. Then you compare acx plus bcy plus c squared and r squared times a squared plus b squared. Be careful to not overflow here somewhere. So always check what the constraints on the coordinates are. And if there's an issue, learn to use 128-bit integers. G++, I think, supports them. If you have a high enough version and like modern enough judging system. For example, Codeforces doesn't support them because it's on Windows. But other judging systems that are on Linux, they usually support them. They are slower, of course, but like if you need to do some comparisons in the couple of places, this is a good choice to learn how to use them. Okay, so we found this point H, and we found the distance from this point H to these 2 points of intersections. Then I can rotate the normal vector, and then I can add this vector with this distance and subtract this vector, so we get these 2 points. An algebraic solution to this will be to just solve the system of 2 equations. And we have that right here. So x minus cx squared plus y minus cy squared is r squared. And ax plus by plus c is 0. So either from the second equation, you can either express x as a function of y, or you can express y as a function of x. So either a is not 0 or b is not 0. So you can express either x or y using this. And then you can plug it into the first equation and you get a quadratic equation on x or on y. So you solve it. And then you can calculate x from the second equation again. So, like, this is a good way if you don't want to remember any of this geometry. Okay, so what if I want to intersect two circles? Have a circle, C1, R1. We have another circle, C2, R2. Okay, so first of all, let's talk a bit about algebra and like to intersect two circles to find these 2 points. We can just solve it with algebra, right? So we have two quadratic equations on x and y. C1x squared plus y minus c1y squared is r1, and c2 squared is 2y squared is 2 squared. So we have a system of two equations, and both of them look like this. So both of them look like x squared plus something times x plus y squared plus something times y is something. So the coefficient of x squared is 1 and the coefficient of y squared is also 1. This means that if we subtract these two equations, then we get a line. Right? So if we subtract these two, then x squared cancels out, y squared cancels out, and we get a line equation. So this will be this line that passes through two points of the intersection. So this will be the equation of this line that passes through 2 points of the intersection. And then we can intersect line and circle the way we did before. The other approach is to do it directly. So let's denote the distance between two circles as d, and denote the distance from C1 to this point that is formed by intersection of this line and the line between two centers as t, and this is h. So this is the height of this triangle. So we can have two equations, t squared plus h squared is r1 squared, and d minus t squared plus h squared is r2 squared. So introducing these two variables, we still have equation with two variables and two unknowns, but we can easily express t from this equation. So let's subtract these two equations. So what do we get? We'll get minus d squared plus 2d times t. H squared cancels out, and we get r1 squared minus r2 squared. So t is r1 minus r2 plus d squared divided by 2d. By the way, if you are trying to be really precise, so in some problems you have to be really precise, there is only one square root in this one square root calculation in this formula. So there's a square root here, and the numerator doesn't have any square roots. Well, then you can find this point by taking this vector, normalizing it, moving t, distance t in this direction, so we get this point h. Now we can rotate this vector, calculate h small, then go into this direction, h, the distance h in this direction, and the distance h in positive direction, in opposite direction, and then we get these 2 points. Okay, so this is about circles, but this is not what I wanted to focus about circles. How do I check? Well, let's check. We have 3 points. So we have a center somewhere here. So this is this looks like a circle that this triangle is inscribed into. So let's have these 3 points A, B, and C. And we have one more point P. How do I check? Is P inside circle what's the word? Like circumscribed, right? Inside the circumscribed circle, A, B, C. Turns out there is a really cool formula that you can calculate in integers. That you can do it the old-fashioned way, right? So you can take the middle one, take the middle points of 2 sides. You can draw the perpendicular line through that point, and the line should be perpendicular to AB. So this is the first line. This is the second line. So their intersection is the center of the circle, and then we can calculate the radius and check if P is inside this radius. And probably there are more like school geometry formulas that can make you check that P is inside here. So this is a rational point. The radius squared will also be a rational number, and thus we can check it all in integers. This kind of check is heavily involved in dolometric triangulation. So there are a lot of checks, like if this P is inside, then we can change some triangles. So this is considered a bad situation. So a dolometric triangulation is the one where if you draw a circle around each triangle, it doesn't contain any other points rather than these 3. So it always exists. There are hard algorithms for finding that. I don't remember a contest problem that required that. Maybe there was a problem on Voronoi diagram that is connected to the Delaunay triangulation, but I don't think that you really have to know Delaunay triangulation to be considered a good competitor. So the cool trick here is introducing a third dimension. So we have like 4 points with x's and y's. For each point, we'll calculate the z value as x squared plus y squared. So you can imagine that as you have a plane. You have some points in it. And you draw this paraboloid that starts at origin. And basically, you take each point and you project it upwards. So, like all points here lie on a paraboloid. So, z equals to x squared plus y squared. The cool trick here is 4 points, 4 2D points are on circle. So there is a circle that passes through all 4 points. So for example, the P might be here. This statement that 4 2D points are on the same circle is equivalent to 4 3D points are on the same plane. 4 3D points are on the same plane. And now we do the same to check. So to check if 3 points are on the same line in 2D space, we check if this determinant ax minus bx, the other way around, right? Bx, ax, by, ay, cx, ax, cy, ay. Well, this is just a cross product. Or there's an equivalent 3D 3x3 determinant, which might be easier to remember, which is just ax. Not sure about the order, but probably doesn't matter. 1 ax ay, 1 bx by, 1 cx cy. So this is how you check if 3 points lie on the same line in 2D space. The same, well, this is easily generalized to 3D, right? So we have 4 points, and the notion of signed volumes, signed tetrahedron volumes in 3D is the same as the notion of like signed triangles in 2D. So we will check if 1 ax, ay, ax squared plus ay squared, bx, cx, dx, y, bx squared plus ay, y squared, cx squared plus cy squared and dx squared plus d squared. So this is 0 if 4 points are on the same circle. This is, and you'll have to see if this is less than 0 if point P is inside, and if this is greater than 0 if point P is outside. I don't really remember, and I might have messed up the order, and it also depends on the orientation of your triangle. So if your triangle is correct, so if the points are in counterclockwise order, so if A, B, and C, like on this picture, then we have one sign, and if you have the other direction, it's the other sign. It's advised to keep all your polygons in the correct order, so the correct order is counterclockwise. If there is a contest problem that tells you that the polygon is given in clockwise order, shame on them. And if it's given in either clockwise or counterclockwise. By the way, there is an easy way to check for even a non-convex polygon what the direction it's in. And it's just, let's calculate the signed area. So by the way, how do we calculate the area? So there are, I think, two most popular ways. We're using triangles and using trapezoids. Which one do you use? Yeah, I think it's triangles, or it's, yeah, I think it's triangles, right? So we have an origin somewhere. So we take this triangle with the minus value, we take this triangle, we add this triangle with minus, then we add this triangle with plus, so this cancels out. Then we add this triangle with a positive sign, then this cancels out. And we add this triangle with a plus sign. Then we subtract this triangle. And everything that's left, that's the area. So just sum from I from 0 to n minus 1, origin AI, cross product, origin I plus 1. And one half of that is the signed area. I think that's the shoelace formula, right? Since if you expand this, you will get something like this. Just a 2x2 determinant when you plug 2 points. So if the signed area is positive, then the polygon is counterclockwise, and if the signed area is negative, then the polygon is clockwise. This is a very easy way to check if the polygon is in correct orientation or not. Okay, so, and the last algorithm before the break is, okay, now we know how to check if we have a circle that it's based on 3 points. How do we check if the point is inside that circle? Now, one of the coolest algorithms in computational geometry is finding the smallest circle that covers all these points. Turns out there is a randomized algorithm, so the cool randomized algorithms are rare, and it can be done in linear time. in expected linear time, of course. Okay, well, there is an easy algorithm in NQ, right? So we try all possible triples of points, we try all possible pairs of points. Sometimes there is a situation where the smallest circle is based on just 2 points as a diameter. This will be also one of the cases in our solution. So there can be a situation where no 3 points, like the smallest circle is built on only 2 points instead of 3. Okay, so if this is a randomized algorithm, then let's shuffle points randomly. Then we will go over the points in, so we have points P1, P2, Pn. We'll go over all these points and try to build the smallest covering circle for just the first point, just first 2 points, just first 3 points, 4 points, 5 points, and so on. Whenever we get a point that's not inside the smallest circle, we'll try to rebuild. So 4. So initially, circle. Let's just create the circle on first 2 points. Circle on P1 and P2. So the smallest circle that contains these 2 points is just a circle where the midpoint of these 2 points is the center, and the distance between them two divided by 2 if the distance between these 2 is the diameter. So we'll add all points from 3 to n. So if the current point is already inside this, then we're done. Then we don't need to do anything. Then the smallest circle for first I-1 points, if it also contains the ith point, then this is still the smallest circle for the first I points. So if Pi is inside C, then we continue. And remember, these points are in random order. Okay, what if it is not? Well, what is the probability that the ith point is not inside the circle, the smallest circle formed by the smallest circle for I-1 point? So what is the probability? Probability Pi does not belong to the smallest circle for P1, Pi-1. Well, let's consider the smallest circle for the first I points. So it includes this one. It must contain Pi on its border. So if Pi does not belong to the smallest circle for first I-1 points, this means that the smallest circle that contains this point must contain this one on the border. Otherwise, we could just delete it, and this would belong to the smallest circle for other points. So the base idea here is the smallest circle always is based on at least 2 points, 2 or 3 points, or maybe more. So let's consider the smallest circle. For P1 up to Pi. So it must contain Pi somewhere. Now, the probability that we're calculating is the same as we took the smallest circle for I points. What is the probability that the last point is on that circle? The last point is on that circle.
1.
Well, if there are 4 points, so if there are 4 points on this circle, this means that if we remove this one, so this must belong to the smallest circle, right? So this have numbers pj less than pi. So if we remove this one, this still belongs to the smallest set. So to calculate the probability of the event where pi does not belong to the smallest circle is, first of all, we'll have to have either 2 or 3 points. Let's say we have 3 points on the circle, and the last point among all of them is I. So we randomly chose 3 points because the order is random. So these 3 points that form the smallest circle are are 3 random indices, and we would like to calculate the probability that this is the last one of them. Well, turns out this is less than or equal to 3 divided by I. Basically, we have 3 points, and we would like to calculate the probability. We have 3 random indices, and the probability that I is among them is at most 3 divided by I. Okay, so is this clear? So the probability that Pi does not belong to the smallest circle for all the points before it is the same as, well, if we consider the smallest circle that includes this point must be on a border. There must be 2 or 3 points on that circle, and the order is random. So the probability that this is one of these 3 points that form the smallest circle is the same as we've chosen 3 random indices from 1 to I. What's the probability that I is among them? Well, it's less than or equal to 3 divided by I. Even less, but sometimes there are 2 points on the circle, but doesn't matter. So the probability is 3 divided by I. So we know that the probability that this if doesn't work is 3 divided by I most. So here we will do a recursive call. Let's find the circle. We'll have one more recursive function that is similar to this one. That we know that Pi must be one of the points on this circle. So we'll have another function that finds the smallest circle that covers the set of points, and we have one more point that must be on the border of the circle. So let's call it F1. So we have first point from 1 to I minus 1, and we have this Pi. So, and let me get here. So F1 of P1, Pi minus 1, and Pi finds the smallest circle that covers P1, Pi minus 1, and Pi is one of the points on the border, and contains Pi on the border. So whenever we make the recursive call to this function, we are sure that this kind of circle exists, right? So before calling this function, this if wasn't true. This means that the smallest circle that covers all these I points doesn't contain Pi. So this means that the smallest circle that covers all of these points must contain Pi on its border, so we have an additional restriction here. So how is this function implemented? Well, we can do the similar stuff, right? So first we make a circle that's based on P1 and Pi. Let's call this somewhere something other way. So let's call this F. Py and F. Then we try all possible points j from 2 to I minus 1. And we try to find the circle again if Pj is inside. See, we don't do anything. And if it's not, well, let's do the same. Let's call another recursive function that, given 2 points on the circle, finds the smallest circle that encloses all the points before it. Let's call it F2. So we have P1 up to Pj minus 1, and also we have Pj, and also we have F. Well, and F2 is easy, right? So we have 2 points as the diameter. And either all the points are inside, in this case this is the smallest circle, or some point is on the border, or if it's outside, basically. So if it's outside, then we rebuild the circle. So I'll leave the implementation of the function F2 to you. The only thing that's left is to prove that this is linear complexity. So first of all, we shuffle all the points, then we build the circle on first 2 points. If we found the point outside of this circle, then we rebuild. We try to find the circle where that point that violated this condition is on the border of the circle. Then this function is similar. So we build a circle on the first point, and this point that might necessarily be on the edge. Then we try all possible points. We check if it's inside, then it's okay. Then, otherwise, we find the smallest circle that contains these 2 points on the border. Okay, so what's the probability that this happens? Well, I claim that the probability that this happens is at most 2 divided by j. Well, the reasoning is similar, right? So we have the smallest circle that contains this point f and maybe some other points, and we get the point outside. So Pj is outside. Let's instead consider the smallest circle that contains Pj and f. So there are either 2 points. So either this is a unique point, so the circle is only based on Pj and f. In this case, the probability is 1 over j. And in the other case, this larger circle is based on like 3 points. In this case, the probability is 2 divided by j. So the probability is that pj is one of the 2 points randomly selected to be on the border of the circle, and the probability is at most 2 divided by j. So now the time to prove the expect. Now, only thing that's left is to prove the expected time, and I claim that f2, well, f2 works in linear time. F2 is just a single pass through all points, and rebuilding doesn't do any recursive calls. So F1, what's the expected runtime of the time of F1? So what's the expected value of the time that F1 takes? Well, the expected time is, well, we can make a recursive call on the second iteration, on the third, on the fourth, on the fifth, and so on. So it's sum over all j from 2 to n. What's the probability that we make the recursive call? The probability is 2 divided by j times the recursive call for f2 on j points, and it's linear, times big O of j. So you can see that j's cancel out, so it's sum of 2 times the constant, so it's linear runtime. In the same way, if we call it this f, then the expected time that function f takes is, again, we sum over all i's from 3 to n. The probability that we make a recursive call is at most 3, well, it's less than or equal, right? Is 3 divided by I, times the runtime for the function f1, which is again big O of I. Again, i's cancel out, so we get big O of n. So this is a strange randomized algorithm that shuffles points and sometimes makes recursive calls, but the total expected time it takes to make all recursive calls is linear. Okay, so that was the algorithm, and it's simple enough, so it generalizes to more dimensions. So we can find the smallest sphere that covers all the 3D points. Just the thing, right? So first, we have to know how to build the sphere on 2 points, on 3 points, and on 4 points. But, if d is a parameter, so this algorithm will now work in d factorial times n, where d is the dimension. So it doesn't work well for high dimensions, but still can be generalized. Okay, so let's have a 10-minute break, and then we will be back with some polygons and half planes and what's the lecture, and I will tell you about the single most important function that you can have in geometry for programming competitions, like clickbait title. So, the one competitors hate him. One weird function. So, let's talk about half-plane intersection. So, a half-plane intersection is we have some number of half-planes that are given usually in form of this line equation, but it's not zero, but it's greater than or equal to zero. So it gives us, so if the normal vector is pointing there, all the points in this part of the plane are good. So the half-planes arise in a lot of places. So for example, a convex polygon is an intersection of half-planes. And if you want to intersect two polygons, that you can just intersect two sets of half-planes. So the convex polygon is just this half-plane intersected with this half-plane, with this one, and so on. So you get it. And a lot of problems can be reformulated to find the intersection of these half-planes, or maybe check if the intersection is empty or not. By the way, these two problems can be solved differently. So there is an algorithm for finding the exact shape of the intersection of these half-planes, and there is another algorithm that can be used to check if the intersection is empty or not, and the second one is easier, of course. So for example, let's take a look at this problem. So we have a set of points. So this is 1, this is 2, this is 3, and this is 4. And we would like to find a spot where so consider this being like trees, for example. So we have tree number 1, 2, 3, and 4. And we would like to find a spot somewhere like here, so that if we look at these trees from left to right, they form the increasing sequence, right? So first, the leftmost tree would see 1, their second tree is 2, the third is 3, and the fourth is 4. This problem can be reformulated to be half-plane intersection, right? So what's the place of points that see the 1-2 pair as the correct one? So we only have to satisfy this for adjacent points, right? So we have to see points 1, 2 in the good order, 2, 3 in the good order, 3, 4 in the good order, and so on. So for all adjacent pairs of points, we need to see them well. And what is the place of all points that see points 1, 2 in correct order? Well, it's this half-plane. What's the place of points that see 2, 3 in the good order? Well, it's this half-plane. And so on. So we have n-1 half-planes, and we need to check if there is a point that we need to cover or not. If there is a point that's covered by all the half-planes, then we can stand in that point and we'll see the correct order of trees. And if the intersection is empty, then there is no such point. Okay, so And another example of the problem, we have a convex polygon. And we need to find the point inside the polygon such that the distance to the nearest side is maximum possible. So we want to find the point such that the distance to all sides is maximum possible. There are algorithms for that, but we can also use half-planes intersection with binary search. So we binary search the answer. We check if is there a point such that all distances from all sides are greater than or equal to x. All distances are at least x. Well, to do that, we can move each side inside by x. And this is a simple transformation on the line equation. This just involves changing the parameter c. So we move each side inside of this polygon. And now we get some kind of new shape. So these are all points that the distance to all sides is at least x. So if it's empty, then we cannot achieve x. If it's not empty, then we can try higher x's. Okay, so first of all, let's talk about the solutions for the half-plane intersection in slower time. So usually, you have some geometric problems, and sometimes the constraints are low enough that you can use some suboptimal algorithms that are easier to code. So, what are these algorithms? Well, the easiest algorithm is big O of n cubed. Right? So you have n lines. You find all possible intersections of all pairs of lines. Then you want to create a convex polygon from these points of intersections. Well, first of all, you have to delete all the points that are not a part of the shape that is a half-plane intersection. Well, what does it mean for a point to be a correct one? Well, this point must be on the right side of each half-plane. So for each, if this point P, for each line I, AI Px plus BI Py plus Ci should be greater than or equal to 0. So there are n squared intersection points. Then for each intersection point, we can check if this inequality is true or not. And then we can, well, now we have all the points that form the boundary of the half-plane intersection. Then we can just, for example, sort them by angle or run the convex hull algorithm that returns the same, returns the polygon but in correct order. So this is n cubed. There is a simple modification that makes it n squared log n. And the modification is, let's try this in random order. Well, there are n squared intersection points. But there are only linear number of points in half-plane intersection in the result. Right, so there's a really large difference between the number of intersection points that we need to check and the number of points in the result, in the final array. Right? Because that's a planar graph, if we consider an algorithm that adds lines or half planes one by one, each half plane adds at most 1 point. Right? So it can cut, so have some polygon, and each half plane can add at most 1 intersection point. So if there are n lines, there are at most n points. So if we check in the random order, then this becomes n squared log n. So we don't just check this for every I. Instead, we'll check for every I in random order. Check for every I in random order. And it's possible to prove that it takes n squared log n on average for random permutation. Okay, now let me tell you about an algorithm that works in n squared. And it involves the function that I really like. Let's call it the cut function. So the cut function takes a polygon and a half plane and returns the intersection of that polygon and the half plane. Again, as a list of points. So we'll get something like this. So we'll do that in linear time. So suppose we have our points P1, P2, Pn, and the line Ax plus B, Y plus C is 0. Let's say greater than or equal to 0. Now we'll form a new list of points that form the new polygon. And this function is really simple. So P and line, let's say A, B, C. So we'll have the result. Initially it's empty. We'll iterate over all points from I from 1 to m. From 0 to n minus 1, doesn't matter. We'll check if pi, so if the ith point is on the correct side of the half plane, then we add it to the result. So for example, we might start here, 1, 2, 3, 4, 5. So if the first point is on the correct side, then we add it. If pi is on, let's just say it's correct, then I add this point to the result. Okay, that was the first part. The second part is, let's check if the segment pi to the next point intersects if the interval, so the end's not included. So if pi to pi plus 1 intersects line L, intersects line, result will add the intersection to the result. So let's look what happens for this polygon. So first of all, we look at point 1. It's a correct one, so it lies from the correct side from this half plane. Then we check, does this segment cross the line? Okay, it does, so we add this line, this point, to the result. Then we check, point 2 is not on the correct side, so we don't add it. This segment does not cross the line, so we don't add it. Point 3 does not lie on the correct side of the half plane, so we don't add it. So this segment crosses the line, so we add the intersection. Now point 4 is on the correct side, point 5 on the correct side, and that's it. So this is how we get this polygon. And how do I check if this segment intersects the line? Well, I'll just calculate the sine distance to that line. So I'll just plug the first point and the second point into the line equation. And and they should have different sides. Right? So if d1 is sine distance from pi to line, and d2 is the sine distance from pi plus 1 to line, then the fact that these two cross, this segment intersects with the line, is equivalent to these two have different signs. Right? So either the first one is less than 0 and the second one is greater than 0, or the other way around. Right? So the second one is less than 0 and the first one is greater than 0. So this is the same as if d1 less than 0 and d2 is greater than 0, or the other way around. So here you probably need to use some epsilons, because if you use the cut function multiple times and the intersection is not an integer point, so you probably calculate intersections in doubles. So since you're calculating intersection in doubles, you need to find the sine distance also in double, and then you need to check it with epsilons. Okay, so this cut function allows us to find the intersection of half planes in n squared time. Okay, so first of all, let's create a large box. So, for example, it can be a square, 0, 0, 1 billion, 1 billion. So that the result definitely fits inside this box. Now, we'll start adding lines one by one. So maybe we have this kind of line. So we'll cut this corner. Maybe we have this kind of line. So we'll cut this corner, and so on. So there are end lines. Adding each line takes linear time. And the cut function is, by the way, what I talked about. So the cut function is really useful, and it's very simple to code. Right, so just check the first point and check the intersection of interval. So boundaries are not included, and it's important so that you don't accidentally add the same point multiple times. Sometimes it might not matter, but this is how you should implement it. So you cut your initial box by these lines. Maybe you have this kind of cut, then you erase this part, and in the end you get some kind of shape. It might be infinite. This means that some part of the original box is still there. So if some part of the original box is still there, this means basically that the half-plane intersection is infinite in that direction. And you want to deal with it somehow. Sometimes you just need the one point from the half-plane intersection. So that's a very easy algorithm to implement, and this cut function is useful in a lot of different applications. So, for example, you can intersect two convex polygons in n² time. Like find an area of an intersection, or maybe do something else. So, and I've used this function tens of times on contest geometry problems, including world finals. Okay, so now let's talk about the faster algorithm. Well, first of all, that idea with a large box is useful so that we don't have infinite parts. So let's add 4 large half planes that look inside. And our maybe real half plane intersection is somewhere inside. Or it might not be finite. Like this. Okay, so the first step of the algorithm is to sort all the half planes by their angle. So each half plane has a normal vector. Let's sort using those vectors. Well, you cannot sort by angle, right? So what does it mean to sort this kind of array? Well, you have to have some starting point. So, for example, you can sort by one additional parameter, which is, for example, 0 if we are in the upper half plane, and which is 1 if we are in lower half plane. So, for example, so let me name this parameter q, for example. So q is 0 if y of that vector is negative, or y is 0 and x is negative. This means that we include this, but don't include this line. So basically the negative x's belong to the lower plane, and the positive x's belong to the higher plane. Q is 1. And then we first sort all the vectors in where q is equal to 0, so that's the upper half plane, and then we'll sort all the vectors where the q is 1, which is the lower half plane. And when you know that all your vectors are in the same half plane, so when you know that the maximum angle between any of your two vectors is less than 180 degrees, so maybe you know that all your vectors point in the same half plane, then you can just use vector product to sort them, right? So one vector is less than another if the vector product is greater than 0. So if the first vector product, the second one is greater than 0, then that's the correct order, since we want to the counterclockwise order. And if you want clockwise, you can just do less than 0. Okay, so that's how we sort the half planes. There can be parallel lines. As far as I remember, it doesn't matter how we sort parallel half planes. It will matter that we, let me think. So among all the parallel half planes, we need to only have the one with the minimum c, right? So if you have 2x plus y is at least 5, plus 5 is at least 0, x plus y plus 2 is at least 0. Well, the second one is a stronger condition. Right? So all the points that satisfy this line, which looks like 2x plus y, 2, 1. So this is, these are these two lines, and we need to take the smaller one. Since we're looking for an intersection of the half planes, this means that we need to only leave the strongest condition there is. So we don't need the first one. If this is true, then plus 5 is definitely true. So among all the parallel half planes, we only need to look at the one with the lowest c. If some half planes are parallel, well, some lines are parallel, leave the one with the lowest c.
But maybe if the normal vectors are not of the same size, you will have to compare it.
Yes. Yeah. With the minimum c, well, if the half planes are normalized, then with the minimum c. Okay. Okay, so now after we've sorted, then we do something similar to the Graham scan that we did before. The same one as in convex hull. In fact, the half-plane intersection and convex hull are dual problems, right? So you can, there is a transformation that converts points to lines and lines to points, such that the half-plane intersection of those points is the same as, well, corresponds to the convex hull of the corresponding points and the other way around. So, for example, the half-space intersection in 3D is the same as finding the convex hull in 3D. If we have enough time after this, I will tell you about how to find the convex hull in 3D in n² time. It's pretty easy algorithm too. So we'll do something similar to Graham scan. Okay, so assume that we have a list of half planes that form the intersection, and now we need to add one more, and maybe we need to remove some previous half planes. So for example, we don't need this one anymore. Well, how do we do that? Well, we need to consider 3 intersection points. So we need to consider this one, and this one. Right? Why this one? Well, for now, let's consider only one intersection point, which was the intersection point between last 2 lines on this half plane. So if it is from the wrong side of this half plane, so if, well, this one is on the wrong side, then we don't need this half plane at all. So we check this and this one is on the wrong side of the half plane, of the current half plane, then we need to delete this. So we do the same, we keep stack of all the half planes, and we delete some, we add the half plane, and then we keep deleting the last half plane from the stack if the intersection point of 2 last half planes is on the wrong side of the current half plane. Well, turns out that it's the same as checking the sign of A1, B1, C1, A2, B2, C2, A3, B3, C3. Well, turns out that checking the sign of this intersection point corresponding to the current half plane is the same as checking the determinant of this. Well, because if we expand this determinant using the first row, then we'll get A1 times B2, C2, B3, C3 plus, minus B1, A2, C2, A3, C3 plus C1, A2, B2, A3, B3. And we check if it's greater than or 0 or not. And if you remember the formula for line intersection, if this is D, this is dx, and this is dy, but minus. So if we divide everything by d, we get A1 times the x coordinate of the intersection point plus B1 times the y coordinate of the intersection point plus C1 is greater than or equal to 0. So that's the same as if we plugged this point into the intersection point into the equation for this new line. So the Graham scan, and if you remember, the Graham scan for convex hull is also checks some vector product, which is also a determinant. if we plug this one, the last one is equal to 1, so this will be the same as the vector product if these three were points, for example. But now we have this new parameter C1. So sadly, that's not it. So it's not enough to just try all possible try all possible half planes once, since the intersection can be empty. So for example, if it looks like this, so that's the first one, second one, third one, fourth one, fifth one. This will still give us non-empty intersection, even though the real intersection is empty. So what we need to do is to run this scan twice for all the half planes. Right? So basically we double the list of all half planes, we do the Graham scan, and we see if any half planes are left. There are some details, but that's the main idea of the algorithm, that we sort everything by angle, and then we try to find, and we use stack, the same as in convex hull, and we remove the bad half planes. Okay, and as I told you, there is another algorithm that finding the half plane intersection is equivalent to finding the convex hull, and the sorting numbers can be reduced to finding the convex hull, and you might already know that you cannot sort faster than n log n using only comparisons of two different objects. So this means that finding half-plane intersection is probably not possible in linear time. But if all the half-planes are sorted, for example, if you want to intersect two convex polygons, then the list of half-planes for the first polygon is already sorted. And the list of half-planes for the second polygon is already sorted. So you can merge these two arrays into one, and then find what is the intersection of all these half-planes. Okay, so now let's look at an algorithm that checks if the intersection of half-planes is empty or not. And this can be done in linear time, and the algorithm is similar to the one with circle cover, and is also randomized. So randomized half-plane intersection check in linear time. So this will tell us, this algorithm can tell us what is the point, what can find us any point in the intersection, in the half-plane intersection, and if there is none, then it will tell us that the intersection is empty. Even more than that, this algorithm will find the point, let's say, with the minimum y. Finds point with minimum y. So again, let's start with the box, and we'll use this point So this is the point with the minimum y. Sure enough. So, and as usual, we will shuffle all the half planes we have. And we'll add them one by one in this random order. So for I from 0 to n minus 1, we want to check if the current point is okay for this line or not. So we check. So we have our current point, so let's call it C is minus infinity 0. 3. So we'll try all possible points one by one, for all possible half planes one by one. We'll check if Cx AI plus Cy Bi plus Ci is greater than or equal to 0. So if there is a half plane like this one, where this point is inside this half plane, well, is on the correct side of this line, then again, as before, we don't need to do anything, just continue. Otherwise, we know that this minimum point for all the lines before this one does not lie in this half plane, so it must be somewhere on this line. So the new point must be somewhere on this line. Now the new best point is somewhere on this line AIBICI. The new point is on line AI x plus BI y plus CI leaves 0. Well, how do we find the point on this line? So for example, we had this line, and we also had this line, and all these lines were good, but then this line came. This half plane. Now we would like to find the point with the minimum y that lies in all previous half planes that has the minimum y. We need to find the point with the minimum y coordinate that is on this line and that is inside all previous half planes. Well, what is an intersection of a line and a half plane? It's half line, right? So for example, if we look at this line and this half plane, it's this way. And if we look at this half plane, it's this way. So now we intersect all the previous half planes with the line. All half planes from 1 to I minus 1 with line, right? So we get a set of half lines, and we need to intersect them all. So we need to find the point on this line that lies on all of these half lines. Well, some of the half lines look to the to the left, and some of half lines look to the right. And so either their intersection is empty, this means that the half plane intersection is empty. This means that maybe we added a line that is somewhere here. So there is this half line, there is this half line, and they do not intersect. But now we find the lowest point on the intersection of these half lines. Find C is the mean point in the intersection of half lines. Okay, for now this looks like an n-squared algorithm, right? So what if we have to intersect all the previous half planes with the current line on every step? In this case, this will take us n-squared time. But since we have random order, the probability that this will happen is at most 2 divided by I. Again, if we look at the shape that our half plane intersection produces, there's a point with the minimum y. And if this line or this line was the last one, then the minimum point changes. And if the last line was one of this or any other line maybe that does not form the intersection, the half plane intersection, then the minimum point doesn't change. So the minimum point only changes when this is the last line or this is the last line. And the probability of that at most 2 divided by I. So there are 2 lines out of I that have to be the last one. So the probability here is 2 divided by I, and again the runtime is sum of 2 divided by I times big O of I is linear. Which is a cool thing, right? So you cannot build the whole half plane intersection, but you can find any point in linear time. And a lot of the times that's what they ask in the problem statement. Right? A lot of the times you need to find at least one point. So for example, in the problem with trees that I told you about, you need to find just one point. And the minimum y here didn't matter. Right? So the minimum y condition here could be replaced with any linear condition. So in fact, this algorithm can find the point with not just the minimum y, but with minimum ax plus by. So for any direction, this algorithm can find the farthest point in that direction. Right? So we intersect of all half lines here, we get a segment, and we take any end of the segment, which one we like more. Well, which one has the minimum ax plus by, or the maximum one? So for example, if you need to find the point with the maximum x plus y, you can do that with this algorithm. So initially you take this point as the maximum one, and then each time this point is bad for a current half plane, you intersect all half lines and take either end of the intersection of these half lines, which one has the maximum x plus y coordinates. Okay, so that's it for half plane intersection. I think this is a pretty cool algorithm, and I like randomized algorithms in general. It's fun to prove that they work correctly and they work quickly, even it might not seem that way from the first glance. Okay, so we have about 15 minutes left, and I think that's enough to tell you about the 3D convex hulls. We didn't talk about 3D a lot, so a lot of 3D concepts like the correctly oriented triples, of vectors are the same as in 2D. So in 2D, we had two vectors that are oriented correctly if the smallest angle from the first one to the second one is produced by rotating counterclockwise. In 3D, it's the same. So we take the second vector and the first vector and the second vector. We look at the direction from the first one to the second one. So if it's counterclockwise, then the third vector must be basically above these two. So if we consider a plane on these two, then it must be above that plane. And if it's counterclockwise, like this, so the third vector must be pointing down. So these are right triples, I think. And there's a notion of an signed volume. And if we have three vectors, again, y1, v1, v2, and v3, or we have 4 points A, and we draw all three vectors B, C, and D. So consider this to be 3D. So like this is higher, and these two are in the same plane. So V1 is B minus A, or BA, AB, and so on. So the signed volume is a 3x3 determinant. V1x, V1y, V1z, V2x, Vx, and so on. And so the convex hull of this point, of some set of points, is now a harder concept than in 3D, in 2D, right? So in 2D we had just the points and the segments between them, and now we have segments and faces. So for example, we can have this lower face, then we have this kind of face, this one, this one, this one, and maybe some face inside. Below all of that. So I'll describe the n-squared algorithm to find the convex hull. This requires a little bit of experience with 3D geometry. So if you don't have that, you might not really get it. So we'll start with finding one segment that belongs to the convex hull. We need our starting condition. By the way, this will roughly correspond to Jarvis' algorithm, which is the gift wrapping. Right? So in gift wrapping, we find the minimum point, then one by one, we find all segments of the convex hull. And here, we'll start with one edge, and then traverse all the edges of the convex hull. So find one edge. Well, how do you find an edge of the 3D convex hull? Well, you can always take the point with the minimum z, for example. One point, the one with the minimum z coordinates. Which one should be the second? Well, that's a hard question, right? So we can look at, so we have this minimum z coordinate, and all the other points are somewhere above it. So we should take the one that has the smallest angle with this plane. Second point, well, it's one of the ways. If you know any other way to find another point that is on the convex hull, that the first point and the second point form an edge of a convex hull, I don't know any easier way to find an edge. So the second point is mean angle from, well, second point is such a point that this edge forms the minimum angle with this z-plane. Such that angle between 1, 2 and plane z equal to z min is minimum. And this, you don't really have to calculate angles. You only need to calculate, for example, the tangent value of that angle, right? So you only need to find the one with the minimum ratio of this distance of z and this distance here. Okay. So that was the hard part. So finding an edge of the convex hull is the hardest part. So now we'll do some kind of DFS. So DFS that takes 2 points, that this is an edge of a convex hull, and it finds the third point that is the third point of a face that contains this edge. So let's, for a minute, consider that all faces are triangles. So this happens, for example, if there are no 4 points on the same plane. This means that all faces of the convex hull are triangles. So this will find the third point on the face, well, with this edge. So we have U, V, and some other point, W. On the face with edge U, V. Okay, let's do it. So, first of all, this is the DFS, so we might visit some edges more than once. In this case, we will mark them as used. So if, let me do it in the beginning. So if used, if visited U, V, we return, and then we mark it as visited. So this is the DFS. In this case, we can visit some edge more than once. In this case, we need to mark it. So for example, there are cycles, and we can arrive to the same edge in multiple ways. So we mark this edge as visited. We'll take some arbitrary vertex of the convex hull first. So W is equal to 1. Well, 1 might be equal to U or 1 might be equal to V. So, well, W is U or W is V, W plus plus. Right, so just I find the first index that's not U or V. Okay, so this is my first candidate for the third point in the same phase of the convex hull. Well, let's try all the other points. So for I from 1 to n, if I is U or I is V, we don't check. And now we need to compare. So we have this edge and we have another point. And we need to check, is any other vertex better than this one? Well, how do I check? Well, it's hard to draw 3D pictures on a 2D board. Well, I have this plane, and I want to check if another point lies to the wrong side of the plane, then this will be my new candidate for the third point in the convex hull phase. So this is my current candidate for the phase. If all other points are from the correct side from this phase, then I'm done. And if some other point is on the wrong side of this phase, then this will be my new candidate. So if I need this function that calculates that 3×3 determinant. Let's call that volume. A, B, C, and D. So if it's greater than 0, then this point will be from the correct side of this half space, and we don't need to change our candidate. And if it's from the wrong side, then we'll replace it. We'll replace W with I. So if volume of P U, P V, P W, and P I, let's say it's less than 0. Again, this does depend on sign. So check if the orientation is correct, or maybe the order of points might be different for you. So if volume here is negative, we replace W with I. And that's it. So now we found the face, which is a triangular face. I can print it, for example. And then I make 2 more recursive calls. So I have found that this is an edge of the convex hull. U, V, W. And then I make the recursive call from this edge and from this edge. DFS of VW and DFS of... Now, VW is useless, right? So since this will find this point, and we need to find other phases. So we need to do WV, the other way around, and we need to do UW. So we'll use this directed edge here, and this directed edge here. So this will find some other point here, and this will find some other point here. And thus we will explore all possible faces of our convex hull. So that's pretty simple algorithm. The first part is the hardest part. Like finding any edge of the convex hull can be hard. Well, this works well when you don't have multiple points in the same plane. Well, more than 3 points in the same plane. And when you have non-triangular faces, you need to do additional checks when this is 0. So whenever you have 4 points on the same plane, you'll have to choose the correct one out of them. And the first phase is also harder. Okay, so and it works in n² time because we have the size of the convex hull is linear. We have some triples, we have some faces, we have some edges. The number of faces and the number of edges is linear due to Euler's formula for planar graphs, but not only for planar graphs, but also for 3D solids. So we have often faces or edges or vertices. So this DFS will explore linear number of edges, and for each edge we do a linear scan, so the total time is big O of n squared. The other algorithm for convex hull in 3D would be to add all the points one by one. So we have some shape in the beginning, then we add one more point, we remove all the bad faces, and we add some new faces. Well, what are the bad faces? Well, the bad faces are for which the new point lies from the wrong side. So, for example, for that back face, this point lies from the back side. So we need to remove that face and instead add these 3 faces. And there is a way to identify which faces are bad. So we keep list of all faces, we keep list of all edges, and we remove the bad faces. We identify which edges have to be connected with the new vertex, and then we add some new faces. This also works in n² because on each step you have the linear amount of objects, so linear amount of faces and edges, and adding 1 point takes linear time. This algorithm can be modified into the n log n1. It's a pretty hard one. It's also a randomized one, so we'll shuffle all points and add them in random order. But there will be some more complicated stuff going here. So if you want, it is available somewhere online. I don't remember where I read about this n log n algorithm, but there is one, and it's similar to the second version. But I think this version is easier to implement, especially in the contest environment. Okay, so any questions about anything that happened here for the last 3 hours? Okay, so if there are no more questions, then the geometry hell is over. Again, just be confident that your geometry algorithms are correct the way you implement them. Geometry problems usually require a lot of code, but a lot of that code is reusable and consists of just standard algorithms. So if you're sure that your algorithms are correct, then you have less places to have a bug in, and you can focus on more meaningful parts of your code. Geometry problems are often intimidating because they have a lot of code, But if most of the code is standard and you're sure that it's correct, then they are not so intimidating anymore. So that's it for today. I was glad to be here to teach you some stuff this week, and I hope you learned something. Today we'll have one more contest, but I'm leaving in a couple of hours, so maybe Ali, who will arrive here tomorrow.
Yes, tomorrow.
Yeah, tomorrow. He will be teaching you next week. We already talked about some topics that he is going to tell you about. So there are problems in today's contest and in yesterday's contest that he will be giving you lectures on. So I think that will be a good start for you to learn those topics. So for example, yesterday's C was solved by, well, the easiest solution that I know uses suffix automaton, and there will be suffix structures as far as I know next week. So again, thank you for listening, and I hope you learned something. That will be the
the way to